Sure.
Good morning, sir.
Everything is fine.
Yes, sir.
And not so prompt and energetic answer. ठीक है सर, चलता है. Anyway, remember some basics of your higher secondary physics from the part of dynamics. Newton's second law, force is equal to mass multiplied by acceleration, or force is equal to rate of change of momentum. It is there. Now, from that relation, F is equal to ma, maybe the motion is given, you need to find out the reason behind the motion, that is the force, or force is given, we need to find out the pattern of the motion. Now, almost similar kind of thing, but one important thing is there. So from the direct thing, when motion is defined, then simply suppose x versus t is given. So find the first derivative, get the velocity, find the second derivative, get the acceleration, equate with the unbalanced force or the resultant force, etc., etc. But for the second kind of problems, when force as a variable is given, then to find the motion pattern, etc., we need to integrate. But as you know, differentiation is rather we feel comfortable. But for integration, sometimes it is giving us some trouble. But naturally, it depends on the engineering application, what we really want to get. So for both the things, whether it is differentiation or integration, we have to be conversant. Okay. Now, force, it may be a function of time, force may be a function of displacement, force may be a function of velocity, etc. So for that simple expression of force, we need to integrate. But one thing is there, that F is equal to m multiplied by a, you may not get that rather relation or equation for your convenience. Okay, so sometime we do in this manner also, that from F is equal to m multiplied by a, we for some cases we can replace a with v dv dx. Okay. Now this m multiplied by v dv dx is a very popular expression. Perhaps you can remember and tell me. क्या रे, मूड नहीं है क्या? Or you all are muted? I don't know. Please let me check.
Hello, sir.
From your school physics, just remember this relation. The acceleration is represented in this form, v dv dx. And can you remember this?
Yes, sir. Yes, sir.
Yes, sir. ওই তো ভিটা dx by dt ছিল, ওই জন্য ওরকম
dx by dt স্যার v
अभी याद आया?
हाँ सर, याद तो आया.
हाँ, नाम क्या है इसका, इस रिलेशन का? What is this and what is this part?
work sir, work done.
Work energy theorem.
Work energy.
Work energy theorem.
Exactly. So not necessarily we need to follow the straightforward manner, mass multiplied by acceleration. It may not be convenient for all problems. So if force is a function of time, force is a function of displacement, force is a function of velocity, different kinds. Suppose a spring force is there, or some friction resistance type thing inside a fluid, that is the viscosity. So for different kinds of thing, different relation you will get, and you need to apply different shape of this expression. For this is the one convenient modification. So here we know this special thing, that is work energy principle or something like that. And from here either directly force is given, you find this, or this one is given, find this. For both the cases, either differentiation or integration, for simple kind of things, you can do this. But for different situation, you need to apply your common sense. And we have discussed about this problem. The object is restricted to move along this horizontal surface. Of course, the direction of the force P is not horizontal, it is inclined at an angle 30 degree. So find the component of the force along the direction of the movement, or you can do in other way, that find the component of the displacement which is in horizontal direction, and that mathematical component of that along the direction of the applied force. So it depends on the situation which will help us conveniently. It is that. Now, after that, we discuss about, either the equation of motion, or in terms of D'Alembert's principle, that is F minus ma is equal to 0. So include this minus ma force here, opposite to the direction of actual acceleration, and write as if it is an equation of equilibrium, but instead of statical equilibrium, it is equation of equilibrium equation for dynamics, so that dynamic equilibrium equation. Then we discuss about this problem. For simple kinematics part, the displacement velocity acceleration for A and displacement velocity acceleration for B, those are related in 1:2 ratio. So whatever may be the acceleration towards right for this block A, simply half of that will be downward acceleration for block B. And these are there either in the form of equation of motion, or you can write down the dynamic equilibrium equation. Next, instead of this horizontal floor or horizontal table, we consider, now in this case, it cannot move automatically towards left. Only possibility is it can move towards right if this weight is having some considerable value which overpowers the friction resistance here. Okay. Now for this situation, here is a 60 kg mass placed on this inclined plane, whose coefficient of friction mu s and mu k are given, connected by a rope passing over a fixed pulley here, and ultimately it passes over a moving pulley, and other end is connected to this fixed location. But that basic kinematic relation is that whatever displacement along this plane, upward or downward, it will be giving us the movement in this block B. If it is traveling downward, inclined downward, then it will be traveling upward with half of that magnitude. So similarly, if it is traveling inclined upward, then actually it will come down vertically. And relation is 1:2. Now the system is released from rest with the cable not loose. It is taut. For the friction coefficient, static 0.25 and kinetic 0.2, calculate the acceleration of each body and the tension T in the cable. Neglect the small mass and friction of the pulleys. Now we need to check the motion by assuming static equilibrium, as if it is in equilibrium. So if it is in equilibrium, so for this one, the hanging block B, this is the self weight corresponding to 20 kg. And for static equilibrium, as if there is no acceleration, it is subjected to these two tension along this rope. So twice T is 196.2. So tension T is here, and utilize that T value here and assume that it is sliding downward. So friction resistance is acting up the plane and tension T is developed here, and resolving all the forces along this inclined upward direction as positive. It gives 98.1, that is this tension, minus the downward component 588.6 multiplied by sine 30 degree, plus this friction resistance which would develop against the direction of movement or tendency for the direction of movement, and we calculate this value. Now, what about the value of maximum friction resistance that can be developed for impending motion? That is mu static multiplied by n. Sorry, actually it should not be n, it should be what? This value r, not this normal reaction represented by n. So it is now, can I erase it here? It's not working. I don't know why. Anyway, that small correction you can understand. So it is 0.25 multiplied by this normal reaction 588.6 is a self weight that multiplied by cosine 30, and this value is 127.4. Okay, and as this friction required is more than the maximum possible friction that can be developed, that resistance, so naturally anything less than that cannot resist it there on the plane. So there will be a natural tendency of motion down the plane. Now from simple kinematics, the acceleration of A is double of the acceleration of B, and we represent in this form a common term small a. So it will be twice A. For B it is A, and for A it is twice A. And naturally for A and B we can write down the equation of motion. For A it is tension upward, then 0.2, that is the for moving the kinetic coefficient friction we need to consider 0.2 multiplied by this normal reaction, then minus this downward component of this force 588 self weight 588.6 multiplied by sine 30, and that is equal to mass multiplied by acceleration, that 60 kg multiplied by twice E. And similarly for B also, the vertical movement moving upward. So for upward direction we can find it. Okay. So minus twice T plus 196.2, that is downward, that is 20 multiplied by A. WB, most likely I have done something wrong. So you should check this, whether it will be 196.2 minus twice T or twice T minus 196.2. There is the resultant direction of the resultant force, and that is equal to mass multiplied by acceleration along that direction. So please check it, and expecting this result. Okay. So such kind of thing. 196.2. Exactly. So please make this correction here, and these things are very common and simple, but only thing there is a possibility of making this kind just when in examination hall we are in little hurry to finish all the questions. So naturally we find very little time to look back and checking all these things. That much time we may not get. So please check my calculations. Now, next thing, before going to this problem, we consider the similar kind of problem here. Here is a fixed pulley. Here is a movable pulley. And simple arrangement is here. At this free end, a block having self weight W is attached, and with this movable pulley, this block is attached with its weight double of this block, 2W. Now definitely it is in static equilibrium. There is no confusion. But if we add any small block here, whatever may be the weight, how much small it may be, it disturbs that condition of equilibrium. Okay. Now find the magnitude of an additional weight Q applied on the left. Here if we place one weight Q, so find that value which will give a downward acceleration A is equal to 0.1 g to the weight W. So whenever we add some weight, naturally it will disturb the static equilibrium condition and it will try to generate some acceleration in downward direction, and that acceleration is 0.1 g, and 2W will travel up with acceleration half of A. And then obviously neglect friction and inertia of pulleys. So find the value of Q which will give us this downward acceleration. This is like that. Now if some tension is here T, so definitely here also will be T, and frictionless, massless, etc. That tension is transmitted all along this rope, along this contact. There is also no loss due to friction. So T plus T for the pulley. Here the tension developed through this weight. Here also it will be twice T because it has no mass. So mass multiplied by the acceleration, that is equal to 0. Whatever may be the acceleration, definitely it will give us the tension twice T. So draw those diagrams. Here total force acting downward is W plus Q, resistance T upward, resultant acceleration A downward. So W plus Q minus T, that is equal to mass W plus Q divided by G multiplied by A. And here it is moving upward. So twice T minus twice W, that is net resultant force upward, and it will give us the acceleration half A. So it will be the mass twice W divided by G multiplied by half A. And these are the simple expressions. For first one, along the direction of acceleration, W plus Q, opposite to that minus T, that is equal to total weight divided by G, that is the corresponding mass, that multiplied by A. And for this one, twice T minus twice W, that is twice W divided by G, that is the mass, that multiplied by half of the acceleration here. And from this equation, we can express in terms of express T in terms of the WQ, etc. and replace A divided by G with 0.1. Okay, and again from equation to T. So why you are doing this thing? Just to eliminate this unknown T, because we do not need this T if it is not asked separately. So we have to find out the value of Q.
Sir, one doubt,
So,
sir.
What doubt?
Sir, here tension has unit Newton and W has mass, sir. How we can subtract it, sir?
Q and W, these are weights.
Okay, sir. Okay, sir.
Okay, this is not mass.
Okay, okay.
Okay, so this is force, this is force, this is mass, this is acceleration. And ratio A divided by G is 0.1. Directly we replace it here, and we need to eliminate this unknown capital T. So express T in terms of other quantities from equation 1. From equation 2, express T in this way, and equate this right hand side with this right hand side and eliminate, or you just find the value of Q in terms of W. Now can anybody quickly calculate this and give me the answer?
21
No, I can give you one clue. That is, multiply this equation, this part with 10. So it will be 10 W plus Q minus W plus Q, and here it will be 10 W plus what? W by 2. So in that case, it will come in terms of a fraction. Otherwise, you can write down in terms of decimal also.
Yes, sir. 20T by 21. It is coming W, sir.
Ratio Q is to W.
Checking. Sir.
One by 6.
1 by 6, exactly.
Yes, sir. 1 by 6.
So 10 W plus Q minus W plus Q, that is equal to 10 W plus half W.
For 6.
Okay, so this 10 W and this 10 W gets cancelled. So here we get 9 Q is equal to 1 plus half W. So this comes here 9 3 simply W over 6. Now, not necessarily that relation A is equal to 0.1G will be given. It may be of any other value, and you may not get this computable value. But whatever it may be, these equations of motion, then elimination of this unknown T. Now, if you are asked to find out the value of T, then simply put the value of Q in terms of W, and in terms of W you can find T. Okay. Things are simple. Apply your common sense. Remember the equation of motion. In some cases, you can utilize conveniently the equation of dynamic equilibrium, that is D'Alembert's principle, whatever you feel comfortable. But this information you need to organize according to your convenience. Okay. Now here is one similar kind of situation. Instead of this pulley connected, or it is free, it can move, it is not fixed like this, but we have changed the orientation in this manner. Just hold a minute. These blocks A, B, and C, they have their individual weights. Suppose these weights are WA, WB, and WC. If those are in the ratio 3:2:1, then what happens? Suppose this is 3W, this is 2W, and this is W. Now, one thing, if we replace this 2W plus W by 3W, and here we have 3W, then this will be a problem of statics. It will be in static equilibrium with 3W and 3W. But for this portion on the right hand side, here we get 2W and W. So naturally there will be some acceleration downward and there will be some acceleration upward. Now, if this location, suppose this point is D. Now, if D is fixed, then downward acceleration for block B will be same as the upward acceleration of block C. But for the situation when D is not fixed, like if it was the straightforward manner, then we could find the acceleration of B downward and C upward, that we could do. But D is also moving. So when D is moving, then what about the real acceleration of B or C?
Sir, it will be relative then. We have to consider acceleration of pulley D also and
So
add or subtract it into convention.
the relative acceleration of block B with respect to D and the relative acceleration of block C with respect to D, they will be same, equivalent magnitude, opposite in direction. So that relative acceleration part we need to consider. And when the system is in this type of thing, that is, it is under motion, so naturally the tension here and tension here, they will be of a common value, and not necessarily it will be 2W plus W is equal to 3W. So naturally the tension here is not is equal to 3W, but weight 3W is acting here and it is moving downward. So we need to find out the acceleration of block A, acceleration of B, and acceleration of C. Of course, acceleration of B with respect to D and acceleration of C with respect to D, they have that definite relation, equal value, opposite direction. Now you assume any acceleration A, B, AC, and utilize that relative acceleration of B and C with respect to D. So with all these known information and developed relation from your common sense and utilizing either that equation of dynamic equilibrium or equations of motion, we can find out the individual acceleration for A, B, and C. But whatever acceleration of A, it is the real acceleration, not the relative acceleration. But for B and C, we first calculate that relative acceleration, then utilize with the other variables, we can find it. So a simple modification to that pulley system, it gives us no additional weight like this, but for this portion in motion, it changes the tension. Otherwise, if 2W and W were added and it was hanging from this, it would have been a problem of statics. Okay. Now, kinematics portion is the first step to get the relation, and here we do such simple kinematic relation for this particular problem. here is a fixed disk. A disk is there on which some groups are made or some arrangement is there so that it can rotate about its center, and one rope, not negligible dimension, which has got very small, but you have to consider it, rope thickness or diameter of this rope is d, and the disk is rotated in this way so that this rope is, there is some winding up like action, and what happens as you rotate it, we include more and more length of the rope here, but it is not a simple circle of zero thickness. So to consider the thickness of this rope or the diameter of this rope for this particular problem, that whenever you make one complete turn, this weight shifts laterally. For one turn, it shifts by d distance. So in this way, if it is making one complete turn, then it is not joining this end. It will take simply a position beside it of that same thickness d. Intentionally, I have made this, kept this white space there, but actually all these blue lines will be connected together, but in that case it will be a thick circle. So just to avoid that confusion, I kept very thin space there. Okay, so that we understand that when we complete one turn, there is a lateral shift of magnitude small d. Then the second turn it completes and it comes here in this position. Similarly, when it completes the third turn, it is here. So that lateral shift of this weight of very small magnitude d radially, it is neglected. But genuinely it has got some effect, because whatever may be the angular velocity, fixed omega, then what about that linear velocity r omega? R is changing. Here is the minimum R, then R plus D, R plus twice D, R plus thrice D, etc. So as the radius changes, the linear velocity also changes. So from that change in linear velocity, we can find out the acceleration of this. Okay. Now, other information like this: a weight W attached to the end of a small flexible rope of diameter D, 1/4 inch. Now these units are not meter, second, etc. So this is in inches. So rope diameter is 1/4 inch, is raised vertically by winding the rope on a reel. If the reel is turned uniformly at the rate of 2 rotations per second, what will be the tension S in the rope? Now, how to get the angular velocity omega from this RPS? Two complete turns per second. So per second it travels 2 multiplied by twice pi, that is 4 pi radian. So omega is 4 pi radians per second. Now what will be the tension S in the rope? Neglect inertia of the rope and slight lateral motion of the suspended weight W. Acceleration is dv dt. This linear velocity changes, that is corresponding to r omega. Omega is fixed, but there is some change in radius dr dt. Now omega is 4 pi radian per second. And what about dr dt? In 1 second, it completes 2 turns, 2 revolutions per second. So in 1 second, when it completes 2 turns, the radius increases by 2 such rope thickness, twice d. So it is twice d inch per second, that is dr dt. So what about acceleration? Put it here, omega is 4 pi, that multiplied by twice d, inch per second, radian per second. So get inch per second square. And in a standard form of that unit, feet per second square, 8 pi d divided by 12. Okay. And what about the tension S? Upward tension will be more than the self weight W. So S minus W is mass multiplied by acceleration.
Yes, sir.
Okay, so find the tension. But this simple information and your common sense, you have to accommodate in this problem very nicely, because this radius changes. It is not simple rotation continuously. So this part dr dt, it is given in terms of that 2 turns per second.
By drdt is equals to 2d.
Original radius was here. After 1 second, it comes here. It completes 2 turns, 1 turn, another turn in 1 second. So it in 1 second, for 1 turn, it increases by d. In half second, in another half second, it makes another turn. So it is that thickness t. So gradually you will find it is spiral like thing. Okay, or in this way. So gradually this object shifts laterally, and the first turn it increases by the thickness of the rope. For second turn, it increases again by the thickness of the rope, this d. So that simple information which you need to accommodate. But it is not 1d per second. It is 2d per second, because in 1 second it completes 2 turns. So maybe such kind of thing we may get. But this equation of motion, or S minus W minus mass multiplied by acceleration, whatever it may be. So similar kind of problem, naturally you can take up from any book, and please try all these things. So wherever you get stuck up, you just discuss in your batch, because you'll find so many other, for that particular problem, maybe you will find some better friend there. So the primary relation equation of motion. So either motion is given, find the force, or force is given, find the motion. So either it will be straightforward manner, the differentiation, or in the reverse manner, that is the integration. This is another form of expressing this acceleration or rate of change of momentum. And later we will try this very well-known application, that is work energy. And one more is that there is impulse momentum. So once you know very confidently about all these problems of different manner, different variation of force, it may be a function of time, displacement, velocity, etc. So please do that thing. And one such simple kind of problem that is corresponding to spring. So that spring problem that you can use very efficiently that work energy principle. Okay. Anyway, before moving further, we just take the attendance.
So next day, can you show some examples on how to apply work energy theorem on spring systems?
Sure.
Okay, sir. Thank you, sir.
But before that, this preliminary kinematics part for a single particle, a curvilinear motion, then connected particles, their kinematic relation, and the kinetics part, either using the basic thing what you know from your schools, that is equation of motion, or rearranging that equation in the form of equation of dynamic equilibrium. Sometimes we feel comfortable just equivalent to solving static equilibrium problem. And we can draw
Okay.
the diagrams or the vector diagrams for that equilibrium also. Okay.
Yes.
So a simple modification of this equation of motion, our application in terms of the work energy principle or impulse momentum, impact, etc., that we can find. So please have some practice. Okay then.